Recording. Okay. All right, Zach, are you ready?
Yeah, ready whenever everyone else is.
All right, great. So let's get started then. So our next speaker is Zack Tripp from Vanderbilt University, and he's going to be speaking on the log-concavity of the k-colored partition function.
Thanks, and thanks for having me. So first of all, if you don't know what log-concavity or k-colored partition functions are, no worries. I will be going over both of those. I also want a quick mention before I get started. This is all joint work with Katrin Bringman, Ben Kane, and Larry Rowland. Great, so first I'm going to go ahead and start off with what is a partition. So partition is just a sequence of positive numbers that adds up to some number n. And we let p of n denote the number of partitions of n. So for example, 4, we can get 4 by doing 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, 1 plus 1 plus 1 plus 1. So p of 4 is 5. Importantly for partitions, in some sense, they are unordered. In other words, 3 plus 1 is the same as 1 plus 3. And essentially, this is kind of encapsulated by this inequality right here. Okay, so what we'd like is a nice formula for p of n. And you might think that there should be one because, well, you know, this seems like a relatively simple combinatorial object. Turns out that, well, there is a formula. It's a little more complicated than you might expect, though. So first of all, Hardy-Ramanujan in 1918 gave this asymptotic. Essentially, it's 1 over n times e to the square root of n. Yeah, I'm leaving out a few constants. But you should think of this as a sub-exponential. And it's maybe a little more complex than you might have expected, but this is still a nice, really nice asymptotic. And in fact, Hardy and Ramanujan actually gave a full asymptotic expansion. It was only asymptotic, in other words, not an exact formula. But Rademacher in, I believe, 1937, made this an exact formula. So this might look a little complicated, but it turns out that, well, it is a, you know, it's an infinite series. You have this a sub k of n is a sum of roots. I won't say exactly what it is. And then you have this derivative of something like 1 over square root of n times sinh of square root of n. So it might seem like, oh, wow, there's a lot going on here. You couldn't possibly do anything with it. But actually, I believe Hardy and Ramanujan used this formula to compute p of 200, or rather use their equivalent of this formula, and an explicit cutoff. And the nice thing is that, well, essentially, if you have explicit error bounds, if you find that the error is less than a half, this is an integer, p of n. So if you're within 1/2 of the integer, you know what that integer is. I believe they made McMahon compute it by hand using a recursive formula for p of n, which is very, very complicated and took a while. But point being, we have this exact formula, and you can actually use it to compute p of n. What's also interesting is you can actually use it to prove properties of p of n. So in 2013, de Salva-Pac used a kind of explicit version of this formula, or rather, you know, a version with the first few terms and explicit cutoff, to find this inequality: p of n squared is greater than or equal to p of n minus 1 times p of n plus 1. So this is what's known as log-concavity. In other words, if I took log p of n, this would be the statement that that sequence is concave. Only starting past a certain point, but still. So this log-concavity is really interesting in combinatorics in general. There's a few different reasons for that. One is that, well, if the numbers are positive, it actually implies unimodality, for example. There's also a lot of nice combinatorial proofs showing log-concavity of certain sequences. You can kind of think, you know, you're multiplying 2 p of n's over here. In some sense, you're combining 2 partitions of n on one side, and then a partition of n minus 1, and a partition of n plus 1, and somehow this set should project onto this set. So this really does have a nice combinatorial interpretation, and there are combinatorial proofs of log-concavity for a lot of sequences. All All right, so another interesting inequality that's satisfied by P of n is this one by Besenrad-Odo. So it says, except for a few different, a few small choices of A and B, P of A times P of B is greater than or equal to P of A plus B. So again, they use this effective version of the exact formula above to prove this. And both these inequalities are, very interesting in their own right. And one thing that they both do is they're kind of combining additive and multiplicative properties for the partition function, which can be difficult to do. So that's part of why they're so interesting. And they also inspire a lot of follow-up work as a result. So, for example, this first paper is follow-up to Besenrad-Odo, and I believe they show a similar inequality for something called overpartitions. This second paper, they give actually a combinatorial proof of this. It's really pretty, so I'd recommend checking it out. And then Chern, Fu-Tang, and Heim and Neuhauser go and extend this, give a conjecture rather, for how to extend something like this for what are called K-colored partitions and fractional partitions. So let's go ahead and define those. So for those of you who maybe don't know, the partition generating function has a very nice series representation. We multiply 1 over 1 minus qtn. And the way to see that this is the generating function for P of n is you write each of these terms as a geometric series and essentially ask what are all the ways you could sum up to the power of n. Well, you'll see that you're just doing partitions of n. And so if we go ahead and just take the alpha power of the right-hand side, this is now going to be a Q series. We might not know what it looks like yet, but we do know it'll have, some coefficients, and we call those p sub alpha of n. This is going to be the fractional partition function. The idea being, we're taking a fractional power of the partition generating function. One thing I want to quick point out, this is a pretty easy observation, but this is something I want you to keep in your mind for near the end of the talk. Notice that the generating function for p sub alpha sub 1 and p sub alpha sub 2 is, if you take the product of those two, is p sub alpha 1 plus alpha 2. So again, this is pretty easy observation just because you're taking alpha 1 power and alpha 2 power, multiplying them, you add the powers. But I'll come back to this fact near the end of the talk. Okay, so why do we care about fractional partitions? Well, for one thing, I should say there are a lot of nice formulas involving them. So for anyone who's maybe seen it, Nekrasov-Akunkov is something that talks about essentially a statement about fractional partitions and relating them to hook lengths of partitions. But even simpler than that, well, if we let alpha equal k be a natural number, so throughout the rest of the talk, I'm letting alpha be a real number and k represent a natural number, there's a nice way to interpret this combinatorially. Namely, you're just doing partitions, but now you're allowed to color the parts. So to see what I mean, well, there are only two partitions of 2 and 1 plus 1. And the two colored partitions, though, you're allowed to say, well, you can have a black 2 or a red 2. You could also have 2 black ones, a red one and a black one, or 2 red ones. And so p sub 2 of 2 equals 5. So notice this comes up actually pretty naturally in combinatorics, because if you're just trying to study partitions, but it turns out the things you're the things you're allowed to sum up are coming from k different sets, that's a k colored partition. So these are quite natural to study. Okay, so I mentioned those nice properties of the partition function before. And it turns out we have two conjectures that are of similar nature for the k-colored partition function and the fractional partition function. So first, Chern, Fu-Tang in 2017, they proved some properties of the k-colored partition function, and then they conjectured this. P sub k of n minus 1 times p sub k of l plus 1 is greater than or equal to p sub k of n, p sub k of l. So again, the way I like to think about this is a nice mixing of additive and multiplicative properties for the k-colored partition function. It's pretty natural from the kind of Besenrod-Ono and the log-concavity as well. And then Hyman Neuhauser earlier this year conjectured that this is still true for fractional partitions. In other words, it didn't matter that this was k-colored partitions. You can replace this with a real parameter alpha, and it's still true. I will say this isn't quite right as I've stated it. You have to make a slightly larger exception set in this case. Feel free to check out our paper if you're interested in that. But more or less, it's the same thing though. Okay, so my collaborators and I were interested in this inequality. And so what we did is we took left-hand side here minus the right-hand side and studied what has happened asymptotically for fixed, well, real number alpha. And here is what we get. So we, I should say, capital N is just a slight renormalization of little n, and capital L is a slight renormalization of little l. But what this is saying is that, well, as long as L is bigger than some number, just depending on alpha, then this this number that we're interested in, this thing we're trying to show is greater than 0, is, well, there's all these terms, but more or less what I want you to think is that this whole thing here is the main asymptotic for this difference. And then what we multiply by is what, kind of the main work of my co-authors and I is, well, this is the main asymptotic, but we also get an explicit error bound for the remaining terms. In other words, what we say here is that past this point, the terms are 1 plus something that is some function whose absolute value is bounded by 2/3. So again, finding this main asymptotic isn't too difficult, but what a lot of the work went into was trying to find an explicit bound on the remaining terms. Okay, so first I want to just give an idea of where we got this from. So we have this theorem from, I believe these were UVA RU students from a year ago, and they prove an exact formula for the fractional partition function. This might look like there's a lot more terms, but in fact, this is pretty similar to the exact formula of Hardy, Ramanujan, and Rademacher. We have these A is kind of sums of roots of unity again. We have some like square root of n, etc. The main difference here is that instead of taking a derivative of sinh, you are now looking at something called the I-Bessel function. Due to time, I'm not going to really get into what that is. I just want to say that it is a well-studied solution of a differential equation that comes up pretty naturally in modular forms. And so, we know a lot of properties of it. And so what we did to get our result is, well, the main term comes from m equals 0 and k equals 1 in this equation. And so then we explicitly bound all the remaining terms. Explicitly bounding the remaining terms is maybe not as easy as just what I said, but still, it's something that can be done using everything we know about the Bessel function and this sum. The thing is, even when you have the main term, you have, if you plug in k equals 1 and m equals 0, you get something that's much simpler than, well, this looks like. You still, though, have to do okay amount of bounding, though, to find, kind of your main asymptotic, but everything in some sense is fairly elementary and explicit. It just, you have to take quite a few terms because there's actually okay amount cancellation in our equation. Okay, so all that to say, we use another exact formula, this time for the fractional partition function, to obtain this asymptotic. And so the important thing about this asymptotic, and this is, really what motivated us to do this, is that yes, we know the main asymptotic term, but the nice thing about this being effective is that, well, we might not know what this is, but we know it's between 1/3 and 5/3. So regardless, everything here is positive. So we are able to conclude that as long as L is big enough, we have the statement of the conjecture. Okay, great. And this is for any real alpha bigger or equal to 2. Okay, so this is interesting enough. This is, I think, good progress towards the Hyman-Neuhauser conjecture. And one nice thing is that for a fixed alpha, well, essentially all we've left is finitely many cases to check. So, okay, so that leads us to go ahead and check like 2, 3, 4, and 5 by computer. Okay, so you think maybe the next result should be that, well, Chern-Fu-Tang conjecture is true explicitly for 2, 3, 4, and 5. But turns out that actually we were able to prove the entire conjecture just using this corollary and some computer checks. All right, so that's what I'm going to spend the next couple of minutes talking about is how do we get from this step where for a fixed alpha you can do a computer check to how do you prove this now for all natural numbers greater or equal to 2. Okay, so again, how do we computationally obtain the Chern-Fu-Tang conjecture? Well, okay, so as I mentioned, we start with 2, 3, 4, and 5. I will say, I'm just going to say it's a computation check. It is a lengthy one. For k equals 5, it took 71 days. And this is after, in our paper, we talk about how to do some memory saving and some time saving. So this is a, this is a lengthy check, but it's not difficult per se, though. And so now to see how we obtain the result, I'm going to claim that from here, we can actually conclude the result for all k. And I'm going to rewrite our inequality in a couple different ways. So first of all, just by dividing by a couple of the terms in the inequality, we can rewrite it as p sub k of L plus 1 divided by p sub k of L is greater than or equal to p sub k of n divided by p sub k of n minus 1. Okay, so we've just kind of moved around the inequality. The way I like to think about this is what this is saying is this is a ratio of consecutive terms, and so is this. And so what this inequality is actually saying is that if you take the ratio of consecutive terms, that is decreasing as the sequence goes on. And so in order to check that the ratio of terms is decreasing, it's the same to just show that the ratio of terms that are right next to each other are decreasing. In other words, we can take L equals n minus 2, and it suffices to show that. Well, if you take L equals n minus 2, you get this. And if you now move it all back around, this is the same thing as log-concavity. So it turns out the conjecture the entire time was the same thing as log-concavity. Okay, and this is where we get to what I think is the really interesting part. Log-concavity is preserved under convolution. And it turns out that multiplying series is a form of convolution. So if you have, k sub 1 colored partition function is log-concave, and k sub 2 colored partition function is log-concave, then when you sum up those two colors, that one is also log-concave. And so we do, it is important here, I am saying k greater than or equal to 3 because we have this weird exception for k equals 2. But once we've computationally checked 3, 4, and 5, well, every natural number greater than or equal to 3 is the sum of 3, 4, and 5 in some way. So now we've checked them for all colors. Great. So I think that's quite a nice little, just a little tool to use right at the end. And it really makes this thing that, well, analytically, we can't really access these these small values of L and N, but then somehow just doing a few computations and we're able to prove them for even large K. Okay, so I want to quick just finish up on a couple of possible follow-up ideas. So one is that we, give this analytic proof for the log-concavity of P sub K. As I mentioned before, it really is a combinatorial property. There's this nice survey paper of Stanley on unimodality and log-concavity in combinatorics. And you can see a lot of techniques there to how to prove these things combinatorially. So I think that'd be really interesting. Another is that our conjecture is inherently only works for kind of a discrete set of alpha. Like, in other words, we could do a computational check to prove it for, let's say, the P sub 3.5. But there's not really any ways to get it for like intervals of alpha. Like we don't have any way to prove it for piece of alpha for alpha between 2 and 3. So it'd be interesting to come up with techniques to do that. And then lastly, there's a lot of higher order inequalities we could use these same techniques for. So for example, there's the Tehran inequalities. And you could kind of use the same, I think you could use these same methods to prove the degree 3 Tehran inequality, for example. So that would be interesting to do. All right, cool. Thank you.
Great. Let's thank the speaker. Questions?
I have a couple of questions.
Yeah.
Anyone else has? Okay. So I have one comment and one question. So I think for the log concavity definition, the inequality was an square greater or equal to an plus 1 times an minus 1.
Yeah.
The case is inequality is other way.
Say again.
So in the definition of the log concavity,
Here I'll go up to that.
Square, for your case, I think you're getting other way, right? The equality.
I think it wasn't that I was getting the other way. I think it was shifted by n minus. So it's n minus 1 squared now, and then n times n minus 2.
So yeah, I see.
Yeah. So I think it was just shifted down by 1 just because of how I just wanted it to match up with how this inequality was written. So I took L equals n minus 2. But you're right, it is slightly different.
And the second question is, I think, there is so for the partition, Igor Peck and DeSalvo did that. And there is a paper by Madeline Dicey and Riyad Masri for the SPT function.
Yeah.
I think the main, the technique is same. The main difficulty was to get an effective error term on the asymptotics, right?
Yeah.
And for the partition function, they have ready, but for their paper, Masrians, they have to polish the result of Nick and Scott Algren, right? They have to So for your case, do you need to polish the error term to get this result, or you can manipulate the existing asymptotic of the K color partitions, or you have to improve the error terms?
Oh yeah, so we sorry, so I'm not sure if I quite understand. Are you saying do we use pre-existing error bounds, or are we
so did you have to polish the error bounds to make sure the inequality work, or the pre-existing error bounds work on there?
Yeah, so pretty much all of the error bounds are new in our paper. So we do some explicit take the I-Bessel function, expand it out 4 terms, and then bound it from there, and things like that. None of it's particularly complicated in theory, but they are all new bounds.
New bounds. And did you have some better savings, your main terms and the error term give you better saving than the pre-existing, or the same on the same range?
Yeah, so we had some error so there was a lot of so we essentially got rid of all the terms that weren't m equals 0 and k equals 1, and those all have an exponential savings, which is nice, or at least the ones that are k bigger than 1. In other words, you get a lot of exponential savings from just the Bessel function itself, but then you also have to do some error bounding in the Bessel, you have to expand a Bessel function, and that has a lot of
you have to extract a lot from there to get.
Yeah, there's a lot of cancellation going on in there, which is why we have to expand it out quite a bit. So yeah, does that kind of answer your question?
Yes.
Okay, great.
Yeah, I the reason I asked, because for when I listen Daisy's and I think Daisy's talk, and see, they need to redo the error term what Scott Algren. Yeah. So I know this is a kind of nice work actually, by the way. Yeah.
Thanks.
Other questions? So I have a question. So I apologize if this was covered in your answer to Arindam. I don't know all the details of that, but kind of a big sort of picture. When you prove this error that's less than or equal to 2/3. So I guess 2 questions. One, could you refine it into an asymptotic if you wanted? But also, does that error Like basically, does it come from getting things to cancel, or does it come from bounding the absolute value of the things?
Oh yeah, good question. So it comes, it definitely comes from bounding absolute value of things.
Okay.
Really, what the reason the reason you're taking so many terms of the best function is because there is so much cancellation initially that you have to take like 4 terms just to get to the main term, and then from there you're just bounding the absolute value. So and it's because you're taking like products and then subtracting them off of relatively similar ordered things. So but yeah, and then sorry, your other question was oh, could you get this yeah, I think you could probably get some asymptotic results out of this too. Of course, like our main motivation was let's get explicit error bounds that eventually we see it's positive. But yeah, almost certainly you could. Yeah, I mean, even from what we've written down, you could certainly get like next handful of terms, and you could probably get an infinite expansion from it if we thought longer about it. Obviously, we already have an exact formula for the partition, for the fractional partition function, so I'm not sure how helpful that would be, but I think we could definitely do it though.
Okay, great. Other questions? Okay, well, let's thank the speaker again.
Thanks.
So we start again in 3 minutes. So we have Josh Males here, and we have Sudhir Pujahari in room 2.